Hello, thank you all for joining us. We're going to give it a few more minutes yet for a few more attendees to join us, and then we will get the webinar started here briefly. Based in the Minneapolis-St. Paul area. We are pleased to present this series of webinars Midland has developed. These webinars are focused on high-pressure die casting industry. Midland, along with its sister companies, are all advanced, a 100% employee-owned organization. As owners, we are all dedicated to providing our customers with the highest level of quality products and customer service. I would like to introduce the presenters for this webinar. Larry Winkler is president and owner of Wintech Inc., Die Casting Consulting. In 1996, Larry developed and implemented back systems in chill blocks and die casting, and a year later, working with Midland Technologies, commercialized the product. Larry has over 35 years in die casting industry at 5 die casting companies in a variety of engineering roles. Phil Zabracki is our product engineer here at Midland, where he designs and coordinates all engineering activities. He has 30 plus years in the manufacturing industry, ranging from electromechanical circuit board test units, hydrostatic high pressure valves and pump systems, and now high pressure die casting components, with emphasis in designing, managing, operations, and quality control. If anyone has any questions, please submit your questions via the chat feature. Thank you again, and I will now hand it over to Larry and Bill.
Good morning, everyone. Again, thank you for joining our webinar this month. We are trying something a little bit different, where we have an open forum webinar. And this is the chance for yourselves to submit a question, and any question with in regards to high pressure die casting, and we'll answer those questions as best as we can, and hopefully everyone will get some good information out of the questions that we received today. We've had a number of questions submitted before the presentation here, and we'll continue. We'll go with read those questions. And again, if you have any questions during the seminar, you can submit them through the question box, and if you don't see the question box, the chat box too on the GoToMeeting control panel will work. And anyway, so we'll start with question 1. The first question: are there proven tool coatings that have provided extended tool life against soldering, cracking, wear, and high volume production? So that's a good question. And Larry, if you want to tackle that.
Involved die casting of the pre-noted problem. This question.
There, you're kind of breaking up. Can you
look at first? Take a look at the problem with the problem of the soldering. Everyone's got soldering issues. Everyone I've talked to, at least in die casting, has tried some type of coating to prevent soldering. I've tried it. I've been successful with some, unsuccessful with other coatings. So I would say that a good PVD coating would be advisable and suggested. But I think really to address this question, we really need to step back a minute and take a look at what are the causes of these three, and then are there means and methods that we could use to reduce them. Soldering, of course, is caused by the velocity of the metal and primarily in aluminum. You experience soldering in any of the alloys, but primarily in aluminum, because aluminum has affinity for steel, and it will attack and it will embed itself into that steel. So the first issue would be to try and reduce that soldering, and of course, the metal velocity and temperature are the two culprits involved here. Want to take a look at how do we solve those issues to address the soldering. And the means of doing that would be the proper design of the metal feed system, and then along with proper die cooling. Once you've done that properly, if you have done, it would minimize the problem you have with soldering. It won't address the issues you have with, let's say, a core pin that's soldering up. And in those instances, you can add cooling to that pin that would reduce the amount of soldering you would experience. As far as cracking goes, of course, that cracking is caused by the heating and cooling in the process. That's just inherent in the process. The heating cooling and pulls the fractures. And so, looking at the possibility of moving that or reducing that would be proper routine stress relieving. I myself usually try and run 20 to 30,000 shots on a tool, remove it, and use some means, either thermally, primarily thermally, to reduce the stresses in the tool. That will aid in the reduction of cracking. However, cracking is a natural part of the die cast process. Micropeening can also improve that condition. In other words, reducing the cracking, and again, a means of taking stress out of the steel. And the last area, of course, is wear. And again, time you're running castings in different die cast alloys, the degree of wear that you experience is in relationship to the alloy first. But then again, it also relates back to how have you designed the in-gate system, the metal feed system, how have you properly designed your process and set it up to make sure that you've got the adequate metal velocity to fill cavities in the shortest possible time, but on the other hand, also maintaining a low velocity so that you will not, or as low as possible, so that you don't erode the tool. So that's my answer to that one. You know?
Good. Thank you, Larry. We'll go on to the second question here. How to maintain low runner to casting weight ratio for castings weighing less than 8 grams? And go ahead, Ray.
That's a great question too, and I'm sure the person that submitted this question is probably running the small parts, lightweight castings. Something I experienced and learned a few things. First off, what usually happens in these instances where you've got either larger runners and there is no ratio as far as what the gauge area should be in relation to the casting weight. That's all based on the design and the calculations you would use in running a PQ square to determine what your machine was capable of and what the gauge area is. And of course, that subsequently would lead to the design of the runner and the metal feed system. But I'm pretty sure that the person asking this question is interested in cycle time. And what I've discovered is with small castings, particularly if you're running unit dies in aluminum or in zinc, what happens is the biscuit actually becomes the controlling factor in cycle time. And I've learned that in order to reduce that cycle time, you need very good water control and control of the biscuit temperature itself. Usually a biscuit comes out of the tool about 700 degrees Fahrenheit, and subsequently with a small casting, you're waiting for that biscuit to solidify, opposed to castings already cooled down to the point that you could eject the shot if you had adequate cooling. So my answer to this one is you design your runners and gauge properly, but really in on the temperature control and get control with water primarily in the shot to control the temperature of the biscuit. Excellent.
Say, Larry, with something that small, is that what type of industry do you see? Have you seen castings with that small of a weight?
Usually,
something more.
Yeah, Bill. That's usually in electronics and small components. That's primarily where I see them, and people want thinner and thinner castings. They're always trying to go with lighter weight parts and push the envelope, which is fine, but you're always faced with the fact in cold chamber that you're going to end up with a biscuit, and that's where it's going to be the hottest spot.
Sure.
A lot of times, and I'll just add this, a lot of tools that I designed would include hot oil in the insert itself, which you need for a small part, and then make sure that you run water in the shot block, okay, to make sure that the biscuits cool down. And by the way, you can use thermal analysis to determine with a simulation, determine those temperatures and placement of water lines.
Gotcha. Okay. Good. All right. Well, we'll go on to the next question, and we actually we have one that was just submitted. They're asking about chill blocks and when to use or not use water in a chill block.
That's a good question. Actually, this is my own experience in the years that I've used either chill blocks or vacuum blocks. I have not used any water in them. I don't think it's necessary. I used a lot of them on mag, and of course, magnesium and water don't mix well. And so that was one of the reasons that prompted me to do this. But what I discovered is this: if you design the runner, the outlet runner from the casting cavity to the block properly, you should not have an issue with solidification of the metal in the block or not be blowing any metal through the block. So people that are that retrofit a lot of times do not have a lot of room, real estate, to put in adequate runners to deaccelerate the velocity of the metal from the casting to the vacuum block itself or the vent block. But in most cases, and like I say with me, I've never put her in a block, either vent or vacuum. In all the years I've used them, it all goes back to the design. And if you can do some calculations of the velocity, you would know in the cavity. You should know, I should say, you should know if you've designed the tool properly. You should know what the velocity of the metal is entering the cavity. Now, we all know that that velocity usually decreases because of the configuration of the casting can have a great deal of effect on the velocity as it fills the cavity. And then when it exits the cavity, you can do the calculations and determine what the velocity is at exit. Depending on how you design, if you use overflows or if you use an outlet gate, okay, which I prefer for a number of reasons. But if you use that and design the runners properly and build up the proper amount of resistance in the vacuum runner or vent runner, you should not have a blow through. Therefore, you should not need cooling in the block.
Right. Okay. It looks like another question submitted that with the same from the same person here in regards to cooling the chill block. That indicates here that when we use to cool the block, we get flash around it, and talking about flash around it, but not in the serrated area. So again, I think like you're talking, Larry, that with if you're able to have proper runners to slow down the velocity, then it that can help you with needing to cool down your chill block. And would flash around the chill block, would that have anything to do, Larry, with cooling issues at the chill block?
Yeah, it's possible. Probably two reasons for that: lack of preload on the blocks themselves. The blocks are always, whether vent or vacuum, really should be preloaded the same as the cavities, insert cavities. And then the second would be the thermal, the fact that you're cooling that block down, and it would not be the same height or maintain the same height as the insert. You're cooling the outside of the tool. Usually, I mean, this logic says that I don't want to cool the furthest part or the furthest distance from this would be the cavity now, not the block itself. I know people cool these blocks. When I initially started to experiment with these blocks, I actually put chillers from plastics on the blocks and cool them down. And I was having problems with blow through. And of course, that accentuated the problem. That was kind of the wrong way to go until I learned that, hey, you know what? Little fluidics, a little designing of proper flow and velocities told me that, wait a minute, what you're doing is you just don't have control of the velocity of the metal from the cavity to the block, and that was the biggest issue. So I don't know if that exactly answers the question, but a lot of times in my case, it really accentuated the problem of blow through and flash.
Gotcha.
Cool.
Okay. We'll go on to the question that was submitted earlier. What is the rejection norms in automotive casting, and what is the Ebitda norms in the high pressure die casting business. So earnings
Yeah.
before tax and such.
Right. I guess my comment about that, I've been away from the automotive and what requirements they have. All I know is in general, okay, in general, there are really no norms in specifically for either automotive or die casting. I'm sure different manufacturers, OEMs have the specific, requirements they have as far as what percentage of scrap they can generate. That would be, but to me, that's individual. Every casting is different. Every application is different, and subsequently, you've got to face that. In my opinion, good process, good design, tool design, process design, and then process control, not process monitoring, process control, critical. A lot of people will go in, and I can remember back in the day when, customers were all excited about the fact that we could report the cause of scrap or the fact that we were scrapping casting. My opinion is that I don't want to report it. I don't want to make it. And the only way you can do that is properly design the tool and properly set up your process and to maintain it. It's the way to be consistent. Yield is the name of the game in die casting and or any process that you're manufacturing. But that's my take on that.
Excellent. Okay. We'll go on to another question submitted earlier. Can the metal be reclaimed from the vacuum block? And we've talked about this before, where you can reclaim it from the runner in the block, but the serrated area basically is the same as flash and cannot be reclaimed. Is that your thoughts too, Lair?
Yeah, that's true. However, the one advantage we have, and you could probably get some more. I've never done any quantitative studies to find out what totally could be reclaimed. If you talk to smelters, and I've talked to some about what can be reclaimed, usually anything over 30,000, 25,000 or such can be reclaimed. However, in those cases, in particular at the end of the shot, like we're looking at with the vent, or I'm sorry, the serrated portion of the vent or vacuum, probably would not be in that category because a lot of it is dirty metal, you might say. The rest of it could certainly be reclaimed. One of the advantages of using a serrated block is the fact that they, were thicker than the 5 to 6 thousandths of a conventional vent, and so most of that or some of that could be reclaimed. And it's a much shorter distance in volume. Whereas with a series of vents, if you add them up, you discover pretty quickly that you're losing a lot of metal because you can't reclaim. If you can't reclaim anything over, under 20 to 25 thousandths, then you're throwing a lot of metal away with every shot.
Gotcha. Okay. Good. We have another one submitted, a new one here. Going back to the chill block and with cooling and such, the length and the length of the serrated area, can that affect the cooling if you have say a longer teeth pattern or compared to a shorter pattern?
Mm-hmm. Not necessarily. I guess it could. Just as an example, 390 aluminum, which is a high silicon and pretty free-flowing alloy, at least my experience has been. Abrasive, of course, because it's a high silicon alloy. We've had experiences with die casters running that alloy where a longer block in other words, a longer portion of serration. But the bottom line is this, that as we advertise and suggest to people that you shouldn't really be going over the length of that block, and this is our standard blocks, you shouldn't be exceeding a quarter to a third of that serrated portion with metal. And it should be, by that time, it should be solidified. I have never experienced that, again, not running water, okay, that none of the, unless we had problems with the die flashing and not locking up or something, flash filled it, but no, as a rule, I would say not, if it's going over a quarter to a third of the length of the serrated portion of the block, you have got excessive velocity with your metal. And you should probably take a look at what is your resistance within the design of the runner itself. Extremely critical, to a proper function of the vacuum.
Right. And that kind of goes back to, I think we've talked about this in the past, Larry, with the your output runners, the design of them, a lot different than your input runner. Where your input, you're trying to get a nice flow into your gates, but the idea with the output runners is to try to create some resistance to slow down that metal.
Exactly, Bill. Yep.
Okay. Another one submitted earlier, kind of related to, what is the minimum thickness between die material and cooling channels? And I know that this some of our customers will have their own specs, but kind of what we've seen in the past, an average is that the 3/4 of an inch is kind of a safe distance.
Right.
And this distance from the cooling line to the cavity, but it can vary.
Exactly. And
go ahead.
Yeah, that would vary. Well, first off, it would probably vary, Bill, with the material you're using, your die material, because they have different coefficients of heat transfer. Also, the diameter of the passage itself, and then the media itself. Whether you're running oil, you're running water, that can have another effect. So there's, it's just not a cookie cutter, one size fits all type of things. You can probably the closest I would ever get would be maybe a quarter, but that would be in very, very specific areas, and probably with the oil. We all know that the heat transfer capabilities of oil are less than water. We can really get a lot of BTUs out of a tool running water in comparison with oil. But you can use oil to cool dies also. Like I say, those factors come into play when you get right down to the design of the and location of heating channels.
Excellent. And that kind of leads into a new question that we just had. I think we just kind of hit it. Whether to use hot water or hot oil units for cooling, and again, in some cases, depending on what your application is that the oil can be productive as well. But water, I think I guess I'm not quite sure what the percentage would be as far as using water compared to oil. It appears that it's more popular to use the water.
Yeah, I'd say it was primarily because the hot oil units are expensive for one thing, and a lot of die casters, they're kind of a pain too from from just a process standpoint. On the other hand, what you gain by having good thermal control in the tool makes a difference of making good or bad castings and the percent of yield you get from the tool itself. So lightweight, thin weight parts, magnesium. I ran a lot of cold chamber mag I ran oil in everything we had, and I always had, I'm always to be a little bit maybe conservative. I would put a lot of lines in my tool with the anticipation that if I needed them, I don't have to turn them on. However, if I don't put them on prior to the design of the tool, and I have to put them in later, problem. So you always want to keep that in mind. Engineering is planning. And so if you properly engineer, if you plan ahead and take a look at your casting and the application, you're going to come up, like I said, with good results. Like I said, I ran hot oil in inserts in the whole base to heat it up, and then ran cooling water in the runner and biscuit in the biscuit area and the runners. So a good thermal balance is the key to making good castings.
Right. My hydrostatic days, we used water for most of our applications with the higher pressure. We did use oil for doing some end forming on copper piping and such. You can't get as much pressure with oil, but the key thing too is proper filtering both medias, and you want good clean water. And as I think sometimes perhaps water gets maybe it isn't being filtered properly, and then you can build up issues within your cooling channels and such. So
exactly.
Okay, let's see. Back to our list. So again, we're talking about thermodynamics. What is the ideal part temperature after ejection from the die? Number 6 on our list here. So the ideal temperature, that can kind of vary too on your casting, and you can vary from tool to tool. What would you think, Lair, on that question?
Boy, that's both alloy and part specific. Wow, I don't know. I know most of what I've done in looking at temperatures is that biscuit, because I know that that's the last area to solidify in a tool. So, in thinking of, I've seen tools where we removed the casting, the biscuit was 700 degrees. Obviously, the parts, depending on their size, configuration, wall thickness, had a great deal to do with that. Most die casters will set up in obviously don't want to in cold chamber want the biscuit to explode prior to ejection. On magnesium parts, small parts, the machines weren't fast enough to keep up with the cycle times because they were so short. They were just, so that I guess I wouldn't put impossible in my opinion.
Right. Okay. We have another one submitted just now too. What are the advantages of a vent block over the traditional milled vent, your conventional venting?
Sure. Yeah, Bill, you want to take that one, or you want me to? That's pretty.
Well, I think conventional venting, you can get so much. You can only get so much area out of their evacuation area per runner that you have coming out, and so if you're in a situation where you don't have much real estate, you could put a vent block in, and you could perhaps have one vent block would replace 7 conventional ventings, and so you can buy some real estate with just using a vent block. So that's one perhaps one advantage.
Right. The other thing is, I mentioned before, if you consider the fact, most of the calculations that I've done over the years, and I've done a lot of them, on venting or vacuum, what's necessary, indicate that, and this is something that a lot of die casters have done. I know if you've been in a die casting plant, you know that a lot of times the casting, you'll take a look at it and say, this die this is undervented. So you'll back off the lock, and you back off the locking force of the machine to allow the tool to breathe. And of course, what you're doing is you're allowing the tool to breathe. Good news. The bad news is you've lost pressure on the metal. And I've seen instances where the exterior of the casting looks great, but once you open the part up, it's full of air because you've lost the impact pressure that's required to make a structural or just a casting that has some integrity to it. So that's one area. In most of those calculations, it would indicate that you would need, depending on the size of the part and how fast it fills, you would need a total total venting of the part. In other words, the entire periphery of the part would require venting to do an adequate job. That's based on calculations, by the way. So, as Bill mentioned, so there's a couple of advantages. Not only the fact with a chill block and the serrated pattern, you can reclaim more metal, obviously, because you've got runners going to it. I know the argument has been held that, well, if I'm not going to be able to reclaim as much, and that's not true. In the runners, you will be able to reclaim. The other advantage of the runner and using a block is that everything is together. In other words, a runner is all tied together. I've seen over the years designs where the overflows, the die caster was trying to maintain some cleanliness, thinking that if he tied overflow to overflow with a connection around the periphery of the casting, it would be a benefit. Well, it's true it's a benefit from the standpoint of handling the metal and the scrap. Unfortunately, it's not true in the sense that your chances of making a defective casting go up when you do that. And all you have to do really is do some simulations, and you can do this. I did it on the machine where I intentionally tied them together and then I blocked them off. And we were experiencing porosity inside the cavity. And what was occurring was the pattern of the metal going in and the air was being pushed back into the cavity. So we were going in one overflow through the passage to the next connection, back into the casting to the next overflow. That's also true of large overflows. Large overflows, I know I've seen them hanging on the side of a part, and the likelihood, and I've experienced it, I've known it, I tried it, I've done it as in experiments, and the metal will flow back into the casting before it goes out through a 10,000 or 15,000 thick vent to start with, by the way. Obviously 5,000 atmosphere, but I've seen it over and over. Not a good idea. So that's one of the other advantages, being able to reclaim more material and then being able to handle scrap, plus the fact that you're getting the advantage of adequate venting for evacuation of the cavity.
Right. It kind of relates to one of the other questions submitted earlier. What happens to too much venting, and that can create a loss of metal pressure, which can result in porosity, of course. And so it's good idea to determine your what size vent blocks that you would need, what evacuation you would need per tool.
Correct.
We do have another question here submitted. How do most die casters establish shot parameters on a new tool without any kind of mold flow simulation? That's a good question. That's a
great question. And back in the day, before there was simulation, it was by calculation. That's you run PQ square, you follow NADCA's guidelines as far as designing the tool. We got to the point, if you know your machine, okay, you can get to the point that you can, in most cases, run 90% in the machine first time. Now, a lot of things have to happen in order for that to occur. But if you have monitoring on your machines and a way to control the machine, you'll know what the machine's capable of. So if you know what the machine is capable of, and the machine is just really a clamp and a pump, okay, a means of forcing metal in a liquid into a cavity. If you know those and the attributes of that machine, you can size out the particular job. I had a lot of tools that would not run. The machines were not capable of running particular jobs. And so it's done by a means of calculating the proper parameters necessary when you actually in the design stage. The first thing I do is look at the casting. First thing you do is where do you gate it? And then the next thing you do is what size gate do I need it to fill it in the minimum amount of time. If you get to the point where you can fill a casting in the minimum amount of time, okay, you're likely to get, you will get a good percentage. Like I say, I was up around 90%, and that was prior to the use of simulation. Simulations are very helpful too because they can do a couple of things for you. Obviously, is show you potential problems in the tool, both from a fluid standpoint, the flow pattern, and then also the thermals. But it can be done without a simulation. Today, most tool shops now have simulation packages of some sort, and OEMs are on to the fact that and they require a simulation prior to acceptance of the tool, or see that the die caster has capabilities of performing them. But my opinion is the most you can do to help yourself get a good monitoring system on your machine, know what your machines can do, and if you do the calculations properly, you should make good casting without a simulation. There's still guys doing it.
Excellent. Good. Well, we're getting close to the end here. If anyone has any questions they'd like to submit, we still have a few minutes here that you can go ahead and submit that. Going back to our list before, we've got a few more questions here. Let's see. One of the questions are overflows and vent flash reclaimable? So we kind of hit this already, but the overflows are reclaimable depending on the thickness, but vent flash is not reclaimable. So, and we'll try to get as many as we can here. We'll go on to the next one: how to reduce soldering. And so, Larry, soldering is the the attraction of aluminum to the die, and
right.
What are your thoughts on as far as reducing the soldering?
Yeah, I mentioned that before. That making sure that you've got control of velocity of the metal as it comes into the up to the casting itself, and then proper cooling and process control. You can do a lot of things with spray and cooling. You can we can also do it with the metal velocity and design design of the metal system and your process itself. Two things that, in my mind, are key. A lot of people will use, and I've used, prior to, let's say, the type of cooling that's available today, jet cooling or some means of hydro cooling or conformal cooling in cavities, and being more aware of the fact that you can use those means to reduce solder, particularly on cores, and also on inserts. If you go with conformal cooling, you'll definitely get a reduction there. But proper design and trying to make sure that your velocities within a reasonable range. Because usually what happens with soldering, and by the way, there's only one means that I know of removing solder, and that's do it mechanically. Some people will and have attempted to do it with chemicals. It's difficult to do that. So it's usually time consuming to try to remove it. And again, the previous question was about coatings that would prevent these, these particular problems with soldering. It probably ends up with be a combination. I've done it, running cavities with coating, a PVD coating on one cavity, and running one without, to see the difference. There definitely was an improvement over the one to the other. On the other hand, I've done multiple cores in tools and had problems with soldering, and the coatings didn't improve it that much. The real key there was to cool that pin, and then also to get a handle on what kind of velocities the metal was at as it entered the cavity and impinging on those cores.
Right. And I think we've seen some very good results from some of our customers too, where they have the again with cooling. If you have the conformal cooling,
Right.
Again, it's kind of depends on your pressures too and such. But they've had good results with conformal cooling and with conformal cooling plus a PVD coating as well.
Mm-hmm.
So we had one more question that was submitted. The best way to track die temperature.
Okay.
Yeah.
That's a great question. That's a great question.
Best would be yeah. Go ahead.
Yeah.
Sorry.
Okay. Well, of course, now with thermal imaging, a lot of people will track with thermal imaging or non-contact pyrometers. Contact pyrometers is a whole list of tools that you can use. I always designed spaces for thermocouples in the tool. And really, thermocouples, you don't have to put thermocouples all over the tool. A number of them in critical locations will give you good readings. The problems I always had was with the setup men, not hooking those, first off, installing the thermocouples, and number two, attaching them to the monitors that we use to record temperatures and shot profile and so forth. They're pretty much universal. They all have this capabilities today to do that. So you're finding that that way you have a consistency of location. Thermal imaging is good, of course, because you can do shot by shot. But if you've got it in the tool, at least my opinion, if you've got it in the tool, it's not as critical. You've got spray and things going on that can have an effect on the image themselves. And usually people will use those at startup. They will not do a continuous monitoring. Whereas thermocouples properly located in the tool itself will give you a constant continuous monitoring of the temperatures in that location. And as I said, if you design the tool right and you've done some, maybe some thermal analysis with the simulation, you'll know where those spots will be that will give you the problems in production. That's where you want to locate your thermocouples.
Sure. Good. Well, that appears to be the. We just got one more question. Let's take a look at that.
Okay.
And the recommended die temperature after spraying. And yeah, that I think we kind of talked about that in the past as well. And it's kind of related to your specific alloy and casting configuration. Is there anything that a number there that you can throw out, Larry, or is it difficult to?
That's a tough one. because what it should be, well, if you've done any checking with a non-contact pyrometer and then tried to get it back in the same location, or with thermal imaging, you'll see what the variation is. And I don't know that there's a number that I've ever arrived at. What most people do, okay, and it's like a default back, I'll say. What they'll do is they'll use the spray to control the temperature of the tool and not internal cooling. And the proper way to, number one, not to shock the die, okay, that's one of the reasons for the cracking of a tool and the deterioration of a tool, is because of the thermal shock that the die sees when you spray something cold on it, assuming you've got that set right and you're using a proper spray head, proper location, and atomizing the spray as it comes in contact with the steel, so you do a good job of removing it, opposed to a hose running over it. And I've seen that hose running over the face of the insert, literally trying to cool the tool down. Obviously, you're destroying the die because of that thermal shock. But my contention is, if you do internal cooling, internal heating, internal control of thermals, there actually are, and I'm sure a lot of people are aware of this, there are instances where liquid spray is not being used on dies, but powders and other means, non-liquid means of release agents, because spray is really intention. Its intention is to help release the casting from a cavity. Okay, it's not meant to necessarily control the temperature of the die, although it's used that way over and over and for always. But if you get a good handle on the design of the tool prior to, you only use a minimum amount of spray. I did a lot of research on that. We were overspraying tools and wasting money like crazy, spending tons of money, and it really wasn't, it wasn't making anything better. And just what I did when I was in the plant, and determined that internal cooling, internal temperature control is the way to go.
So Larry, in some cases where you have like a thin wall casting, that if I recall, usually that's you have to have a higher temperature metal for thin wall castings. And then if you try to cool down to spray down that die right after, well, again, you're indicating that could cause some issues then.
Exactly. What you'll do is you end up running bad parts because you've overcooled the die, shot to shot.
Right.
It doesn't take much release agent to, usually to release the part. The other thing that I'll mention this too, Bill, is that a lot of times you can tell with a shot whether it's been over, and you and I have looked at castings that have been oversprayed, either oversprayed or the die caster used too much lube and tip lube, depending on what he's using. And that overspray shows up in the casting. And, see it sometimes by the vent or runner or vacuum runner portions of the shot. So, yeah, it's one of the problems, inherent in the because operators usually, if you're running manually, they're always going to err on the safe side of not sticking the casting, because they don't want to pull that die out and have to remove that casting. So they'll tend to overspray rather than underspray or have good control.
Right. Yeah, and I think we've seen that too. So I think there's still a lot of casters out there that have operators that are manually spraying the dies compared to auto. So, but which is fine. It's still being used.
It is. Yep. Great.
All right. Well, I think we're at that time where we'll end the webinar for today. And we want to thank everyone for joining us today. A lot of good questions, and we hope that it benefit everyone, and you got some good information on from it. And we are planning on having the next webinar coming in March. If you check our website for the announcement and the subject, and we hope that everyone will attend that webinar as well.
Yeah,
Any final thoughts?
Yeah, I'd like to say that anybody that has further questions or would like clarification of anything that we've said, that they can contact Midland direct, and we'll get back to you. If you're having problems, if you're currently running any of our products and you're having a problem, make sure you ask us. We're more than happy to answer any questions and solve your problems, because all we want these products to do is work for you. That's really what our goal is.
That's correct. That's correct. All right. Well, thank you, everyone, and we wish everyone a good afternoon, and hopefully we'll see you come in March. Thank you.
Thank you.
Claire.
You bet. Thank you,
Bye-bye.
Bill.